September 1941. A locomotive dismissed as mechanical suicide hauls 16,000 tons up a mountain grade that broke every engine before it. Critics laughed at its strange wheels and impossible boiler pressure. But when the smoke cleared, the Allegheny had rewritten the rules of freight forever. What fatal flaw did the experts miss, and why did proving them wrong nearly cost everything? By 1940, American railroads faced a crisis that threatened to strangle the nation's economy. Coal mines in West Virginia sat on mountains of unsold fuel. Steel mills in Pittsburgh waited weeks for raw materials. The problem wasn't supply, it was the brutal geography of the Allegheny Mountains. Every freight locomotive that attempted the steep grades between coal fields and industrial cities struggled, overheated, or failed completely. The Chesapeake and Ohio Railway watched their competitors suffer the same fate. Trains that could pull 5,000 tons on flat ground barely managed 3 signed up the mountain passes. Companies doubled up locomotives, burning twice the coal and wages to move the same cargo. Others gave up entirely, routing shipments hundreds of miles out of the way. In boardrooms across the Northeast, executives calculated losses in millions while their best engineers threw up their hands. This wasn't just about trains. Factory workers went home early when steel shipments ran late. Power plants dimmed lights across cities when coal deliveries stalled. The Saturday Evening Post ran features on America's Mountain Problem, interviewing frustrated railroad presidents who admitted they had no solution. One Norfolk and Western superintendent told reporters, "The Alleghenies might as well be the Himalayas for all the good our locomotives do against them." Into this atmosphere of defeat walked Lima Locomotive Works with a proposal so audacious that most railroad executives dismissed it on sight. Chief Engineer William E. Woodard had spent 3 years designing what he called a simple, articulated locomotive. But there was nothing simple about it. The blueprints showed a machine with 8 drive wheels on each side, a firebox the size of a garden shed, and boiler pressure that exceeded every safety standard in the industry. When Woodard presented his design to the C&O board in early 1941, the room erupted in objections. "Mechanical suicide," declared the chief mechanical officer. "A waste of steel," muttered the operations director. The boiler pressure alone, 260 pounds per square inch, was considered reckless. Existing freight engines ran at 200 psi. Woodard's design demanded 30% more, with all that force concentrated on wheel bearings that critics insisted would explode under load. But the C&O had run out of options. Their competitors were gaining ground, and the looming war in Europe promised an explosion in freight demand they couldn't possibly meet. In March 1941, they authorized construction of a single prototype. Woodard was given 9 months and a budget that made accountants wince. The locomotive would be named the Allegheny after the mountains it was built to conquer. The engineers who built it knew one thing for certain: it would either revolutionize freight hauling or become the most expensive failure in railroad history. Woodard's Allegheny broke every convention that governed steam locomotive design. Traditional freight engines followed a simple philosophy. More wheels meant more traction, but less power per wheel. Woodard flipped this logic. He designed a 2-6-6-6 wheel arrangement, 16 massive drive wheels that would distribute weight while maintaining individual wheel power through an articulated frame that let the locomotive bend through curves. The articulation was the first gamble. The frame split into 2 sections connected by a hinge, allowing the front set of 6 drive wheels to pivot independently from the rear set. This solved the problem that had plagued other large locomotives. They couldn't navigate the tight mountain curves without derailing. But the hinge itself became a point of savage criticism. Skeptics argued that the stress of pulling 16,000 tons would tear the articulation joint apart, scattering steel across the mountainside. Woodard's second innovation was even more controversial. The firebox measured 135 square feet, nearly double the size of comparable engines. This monster furnace demanded a new approach to coal firing. Instead of the standard practice of shoveling coal by hand, Woodard installed a mechanical stoker, a screw conveyor that fed crushed coal directly from the tender into the firebox at rates no human could match. Railroad traditionalists hated it. "Real railroading doesn't need machines to do a fireman's job," one union representative complained in Railway Age magazine. But the mechanical stoker was essential to Woodard's third and most dangerous innovation: Extreme boiler pressure. At 260 psi, the Allegheny's boiler operated at temperatures and pressures that would make a standard locomotive's safety valves scream. The steam had to be super hot, superheated to 800 GPa before entering the cylinders. This gave each piston stroke maximum power, but it also meant that every rivet, every weld, every seal was under constant threat of catastrophic failure. The cylinders themselves were enormous, each with a 24-inch bore. When steam at 260 psi slammed into those pistons, the force was equivalent to dozens of cars smashing into a wall every second. Woodard calculated that this violence, repeated thousands of times per mile, would generate over 7,400 horsepower at the drawbar. No freight locomotive had ever touched 6,000. Metallurgists warned that the drive rods connecting the pistons to the wheels would fatigue and snap. Boilermakers insisted the seams would blow. Even Lima's own machinists questioned whether they could fabricate parts to tolerances tight enough to contain such forces. When the first Allegheny began taking shape in the Lima shops, during summer 1941, workers photographed it like a curiosity, certain they were building either a revolution or a very expensive piece of scrap metal. Woodard kept his drawings close and his doubts closer. He knew the real test wouldn't happen in the workshop. It would happen on the mountain. September 29, 1941. Dawn broke cold over the Allegheny Mountains as locomotive H8 No. 1600 stood at the base of Allegheny Grade, steam hissing from every valve. Behind it stretched a train of 160 coal hoppers, each loaded with 100 tons of West Virginia bituminous. The total weight, locomotive and all, 1.2 million pounds of steel, coal, and doubt. Engineer Frank Morrison climbed into the cab, his boots echoing on the metal deck. He'd pulled freight over this grade for 20 years and watched better locomotives fail. The Allegheny's controls felt alien in his hands. The throttle was stiffer, the pressure gauges climbed into red zones that would have triggered emergency stops on any other engine. Fireman Dutch Keller stood beside the mechanical stoker, watching coal tumble into the firebox like black water. "Never fired an engine that ate coal this fast," he muttered. C&O executives, Lima engineers, and a handful of skeptical reporters gathered at the summit 5 miles and 1,300 vertical feet above. Railway Age had sent a photographer. The Pittsburgh Press sent a columnist who'd already written half an article about Lima's folly. They expected drama, possibly disaster, certainly not success. Morrison cracked the throttle. The Allegheny lurched, wheels biting rail, the drawbar yanking 16,000 tons into motion. The mechanical stoker roared, feeding coal at a rate that would have exhausted 3 firemen. Steam pressure held rock steady at 255 psi. The locomotive accelerated, not with the explosive burst of a passenger engine, but with the inexorable momentum of an avalanche. At mile 2, the grade steepened to 1.14%, a slope that had forced other locomotives to crawl at 8 mph, or stall completely. Morrison opened the throttle wider. The cylinders hammered, their rhythm a continuous thunder that shook the ground. The Allegheny speed held at 18 mph, then 20. Inside the cab, Keller watched the water level in the boiler glass, making sure the crown sheet stayed submerged. If it went dry, the boiler would explode. The articulation joint flexed through curves, the frame bending and straightening like a spine. No grinding, no screaming metal, just the smooth mechanical breathing of 16 wheels working in perfect harmony. By mile 4, Morrison allowed himself a glance at the steam chest pressure gauge, 260 psi, exactly as designed. The Allegheny was holding. At the summit, the waiting crowd heard it first, a deep, rhythmic pounding that grew louder until the Allegheny burst into view, smoke streaming, every wheel turning, 16,000 tons rolling behind it like the train was weightless. Morrison eased the throttle back and brought the consist to a gentle stop. 5 miles, 1,300 feet of climb, 23 minutes. It wasn't just a success, it was a statement. The rules had changed. 3 hours after the summit run, while executives celebrated in the C&O offices, maintenance crews swarmed over number 1,600 with wrenches and inspection lamps. What they found sent a chill through the workshop. The triumph on Allegheny Grade had come at a price no one had anticipated. The side rods, massive steel bars connecting the drive wheels, showed hairline cracks near the bearing journals. These weren't surface scratches. Under magnification, metallurgists could see the telltale signs of fatigue, microscopic fractures spreading through the metal grain structure. At current stress levels, the rods had perhaps 50 more trips before catastrophic failure. Chief Inspector Raymond Cole marked the damage in his logbook with a red pencil. Rods must be redesigned or replaced before next heavy haul, he wrote. Current configuration unsafe for sustained operation. The articulation hinge, that controversial joint where the locomotive's two frames met, had suffered equally. The massive pin that allowed the front section to pivot showed scoring marks where steel had ground against steel despite gallons of lubricating oil. The pin was supposed to last years. After one trip, it looked like it had been attacked with a file. Worse, the bronze bushings surrounding the pin had compressed, their carefully machined surfaces deformed by forces the designers had underestimated. Inside the cylinders, engineers discovered steam cutting, a form of erosion where superheated steam at 800 degree Fs had literally carved grooves into the cylinder walls. The damage was millimeters deep, barely visible, but growing with every piston stroke. If unchecked, the cylinders would lose compression, bleeding power and efficiency until the Allegheny became just another struggling mountain engine. The most alarming discovery came from the boiler inspection. Ultrasonic testing, primitive by modern standards but cutting edge in 1941, revealed stress concentrations around the firebox crown. The extreme temperatures and pressures had caused the steel to expand and contract in ways that created weak points. One engineer calculated that after 50 full power runs, the risk of a crown sheet failure, a boiler explosion, would climb from negligible to unacceptable. Woodard reviewed the reports in silence, his face unreadable. The Allegheny had worked. It had conquered a grade that defeated everything else on rails. But it had also confirmed what the critics feared. Pushing steam technology to this extreme came with mechanical consequences that couldn't be wished away. Lima's accountants ran new numbers, redesigning the side rods, replacing the articulation pin with a hardened alloy, reboring the cylinders, and reinforcing the firebox crown would cost $47,000 per locomotive. Multiply that by the 60 Alleghenies the C&O wanted to order, and the price of revolution climbed into numbers that made even optimistic board members nervous. The choice was stark. Accept the risks and order the fleet, or shelve the design and admit that some mountains couldn't be conquered by steam alone. William Woodard had 3 months to solve problems that should have taken 3 years. C&O's operations department was already scheduling freight runs based on a fleet of Alleghenies that didn't yet exist, and the war in Europe was driving demand for American coal and steel to unprecedented levels. Failure wasn't just embarrassing, it was economically catastrophic. Woodard attacked the side rod problem first. The original rods were forged from carbon steel, strong but brittle under cyclic stress. He switched to nickel-chromium alloy steel, a material used in aircraft landing gear where repeated impact was the norm. The new rods cost 3 times as much and required specialized heat treatment, but stress testing showed they could handle the Allegheny's punishment indefinitely. Lima's forges ran around the clock, hammering out replacement rods while machinists worked 12-hour shifts to finish them. The articulation pin demanded a different solution. Woodard couldn't make it stronger without making it heavier. An extra weight at the hinge point would throw off the locomotive's balance. Instead, he redesigned the lubrication system. Engineers installed a pressurized oil reservoir that force-fed lubricant directly into the pin bearing under 40 psi of pressure, creating a continuous oil film that prevented metal-to-metal contact. The system was borrowed from marine diesel engines, another case of Woodard raiding other industries for ideas that railroad tradition had never considered. Steam cutting in the cylinders proved more stubborn. No material could withstand 800 degree superheated steam indefinitely. Woodard's solution was elegant. He lined the cylinder walls with renewable wearing strips, hardened steel inserts that could be replaced during regular maintenance. The strips absorbed the erosion, protecting the cylinder body. When they wore out, a crew could swap them in hours instead of pulling the entire cylinder for repair. The firebox crown was the final puzzle. Reinforcing the steel directly would have made the firebox too heavy and reduced its heating efficiency. Instead, Woodard added a system of stay bolts, threaded rods that tied the crown sheet to the outer boiler shell, distributing stress across a wider area. The stays were made from the same nickel-chromium alloy as the side rods, and each was individually tensioned to precise specifications. Installing them required dismantling the entire firebox, a job so delicate that Lima borrowed boilermakers from the Navy. By January 1942, the first production, Allegheny, number 1601, rolled out of Lima's shops with every fix in place. It looked identical to number 1600, but underneath the paint, it was a different machine. Woodard had taken the critics' nightmares and turned them into engineering solutions. The real question wasn't whether the Alleghenies could work. It was whether they could work long enough to justify their staggering cost, and whether Woodard's fixes would hold when 60 of these monsters hit the rails simultaneously. Between 1942 and 1944, the C&O Railway took delivery of 60 Allegheny locomotives. They were assigned to the heaviest, most brutal routes in the system: the Allegheny grade, the New River subdivision, and the Big Sandy line through eastern Kentucky. These weren't test runs. This was industrial warfare against geography, conducted 24 hours a day, 7 days a week. The numbers told a story that silenced the remaining skeptics. Before the Alleghenies, moving 100,000 tons of coal over Allegheny grade required 14 round trips by conventional locomotives, burning 42 tons of coal in the process and tying up the line for days. A single Allegheny could haul the same tonnage in 6 trips, consuming only 28 tons of coal. The reduction in fuel costs alone paid for the locomotive's premium price within 8 months. Maintenance records revealed something even more significant. Despite the extreme stresses, Woodard's fixes held. The nickel-chromium side rods showed no signs of fatigue even after 2 years of continuous operation. The pressurized articulation pins ran cool and smooth, their wear rates falling within normal tolerances. Cylinder wearing strips lasted 6 months between replacements, exactly as calculated. The stay-bolted firebox crowns passed ultrasonic inspection after inspection, their stress concentrations stable and predictable. Crews who initially feared the Alleghenies came to trust them. Engineer testimonials published in Trains magazine spoke of locomotives that pulled like they didn't know the mountain was there. Firemen appreciated the mechanical stoker, which let them monitor gauges instead of shoveling themselves into exhaustion. Even union representatives, once hostile to the automated coal feed, admitted the stokers improved safety by keeping firemen alert and focused. The war accelerated everything. By 1943, American industry consumed coal and steel at rates that would have been impossible without the Alleghenies. The C&O alone moved 22 million tons of coal that year, much of it destined for steel mills producing tanks, ships, and aircraft. Other railroads took notice. The Virginian Railway ordered 8 Alleghenies. The Norfolk and Western, once dismissive of Lima's design, quietly inquired about licensing the technology, but the Alleghenies' success carried an irony that Woodard himself acknowledged in a 1944 interview with railway mechanical engineer. "We built the most powerful steam locomotive in history," he said, just as steam itself was becoming obsolete. Diesel-electric locomotives, simpler and more efficient, were already appearing on American rails. The Alleghenies would dominate freight hauling for barely a decade before the tide of technology swept past them. Still, for those 10 years, they were unmatched. No other steam locomotive could touch their combination of power, reliability, and efficiency. The experts who called them a waste of steel had been forced to watch as those wasted tons rewrote the freight record books. By 1956, the last Allegheny was withdrawn from service. 15 years after their triumph on Allegheny grade, these mechanical giants were rendered obsolete not by failure, but by evolution. Diesel-electric locomotives required less maintenance, burned cheaper fuel, and didn't need water stops every 100 miles. The economics were brutal and final. Steel that once conquered mountains was now scrap metal, cut apart in salvage yards and melted down for rebar. Today, only 2 Alleghenies survive, numbered. 1601 rests in the Henry Ford Museum in Dearborn, Michigan, its massive frame cleaned and preserved but silent. Number 1604 sits in the Baltimore and Ohio Railroad Museum, an artifact of an age when power meant steam, pressure, and the smell of coal smoke. Visitors walk around them marveling at the size, photographing the enormous drive wheels, but few understand what they're really looking at: the end of an evolutionary line. Allegheny's story raises questions that echo far beyond railroads. Every industry faces the same choice the C&O confronted in 1941: push existing technology to its absolute limit or leap to something entirely new. The Alleghenies represented the perfection of steam, the final word in a century-long conversation about what fire, water, and steel could achieve together. They worked brilliantly, and they still became obsolete. This pattern repeats across history. The fastest sailing ships were built just as steamships made them irrelevant. The finest steam cars appeared in the same decade that internal combustion took over. The most sophisticated typewriters came to market as word processors replaced them. Excellence in a dying technology is still excellence, but it's also a dead end. Engineers today face similar crossroads. Should battery technology be perfected, or should resources shift to hydrogen fuel cells? Should traditional aircraft be refined further, or should development focus on electric propulsion? Allegheny's lesson is uncomfortable. Being right about what works now doesn't guarantee survival tomorrow. The C&O spent millions perfecting steam at the exact moment the future belonged to diesel. Yet there's another way to read the story. The Alleghenies proved that limits exist to be tested, that critics who call an idea impossible are sometimes just afraid of the work required to make it possible. Woodard didn't just build a locomotive. He answered a question that had haunted American railroads for decades. Could steam power truly conquer the mountains? The answer was yes. For 15 years, gloriously, undeniably yes. The real question isn't whether the Alleghenies were worth building. It's this: when you know our technology is dying, do you perfect it anyway, or do you let it fade quietly into history? And if you choose perfection, knowing it's temporary, does that make the achievement more meaningful or just more tragic? What do you think? Is there honor in perfecting the past? Or is progress the only thing that matters? I'd love to hear your thoughts. Please leave a comment below and give this video a like if you enjoyed it. See you on the next one.